I will take this opportunity to introduce you to SS7. Please note, we cannot tell you so much about SS7. There is a lot of content out there, but we can give you pointers that will help you now appreciate what happens in SS7 or SIGTRAN. And today I'll just talk about the OSI model, SS7 and SIGTRAN. The slides that I have here, one of them was created this year. The others were created last year when we were doing Natujenge season 1. So the videos are still there, just in case you're interested to hear more about these tags. So I will go straight, and I'm hoping that I can actually do this in about 15 minutes. I'll go straight to the presentation. For those guys who watched Love the Bytes series, the central message was, in digital communication, the word digital is very important. It means digits. It comes from digits. So in digital communication, all we do, we send digits. But these digits are binary digits. And binary digits are used because of a convenience that they give in terms of representing data within a computer using switches, using the transistors. So a transistor can be configured as a switch, and it can act as a switch, and it can allow the current to pass, and it can allow the current to not to pass. And that foundational concept is what is used in creating logical gates, or the Boolean gates that we create, the NAND gate and all that. And those are the foundational units of computing and multiplication, addition, and all the things that we do. We use such things to create circuitry. So we said one thing is very critical in sending information. If you want a computer to send data from one place to the other, and this data could be an SS7 message, it could be an SMS encoded in an SS7 protocol stack. Now, the key idea is that everything must be represented in numbers. Whether you're dealing with the IP address, they have to be represented in numbers. Whether you're dealing with a port, they have to be numbers. Whether you're dealing with the text itself, each character has to be represented in numbers. And we saw binary, and we saw how that binary information is so complex for us as humans, and we saw how that binary numbers can be represented as hexadecimal, as nibbles. When I say hexadecimal, it means base 16. So if you really want to know 48, you know that this is the first digit is power 1s, and the others are 16s. So you can do 16 times 4, you get 64 plus 8, and you get 72. So the conversions, we covered that. And we said the process of converting your original message into numbers is encoding. And the process of converting the message, once it's received on the other side, back to the original message is decoding. So you have to do that within your code. And we learned so much about that. Now, because messages are sent from one machine to the other, one of the things that you will note is that network communication is not like two computers that are connected to each other. So you have a lot of nodes that are in between. And certain challenges come into play where you have to deal with addressing. And this is why the OSI model was the magical formula of divide and conquer. So it's a reference model, meaning that each layer of the OSI model, there are no real protocols that we know. If I ask you, give me a protocol in layer 6, you probably do not know. Give me a protocol in OSI, not TCP/IP. So the OSI is just a reference model. And the reason is because of something that I mentioned last year, something called protocol wars. There are people who came up with standards and they never saw the light of the day, and people adopted TCP/IP. And that is what we know today. So it defines 7 layers used in education, defines protocols that were never adopted. So we ended up using TCP/IP, which we use to understand. So if you know TCP/IP, one thing I need you to remember after this, SS7 stack and TCP/IP, they're like brothers. So every challenge that TCP/IP tries to address, you might probably find the same challenge being addressed in SS7 differently. E.g., in TCP/IP, one of the challenges that we needed to overcome is every computer on the network must be given an address. And we normally give them 2 addresses. One, the physical address, and the other one, we give it the logical address. Physical address you have heard about MAC address that comes with your network interface card. Logical address is your IP address. And in SS7, we also have equivalents, but we don't use the same thing. So in SS7, you'll never hear the SMSC has an IP address, quote unquote. Now, SIGTRAN was a thing that was adopted to help us carry SS7 messages over IP network. Because IP became so popular, everything is IP, and we needed to transfer the signal over IP. So the SIGTRAN stack also adds protocols that allow us now to bridge between the IP network and the SS7 protocols that are above the transport layer. So I can give you a challenge, which I don't need to mention right now, but I'll mention briefly what happens in these layers in reference to when you're sending a message. Let me give you an example. You want to send hi to your friend from one mobile phone to the other. At the application layer, you have a form, a UI where you can type hi. So once that information comes from the user interface, that information has to be passed to the network to be sent over the network. But before passing, we must represent every H as a character, as a number. So first we use a character encoding scheme. We use UTF-8, ASCII, and the H gets a 72. And maybe the E gets another number or the I gets another number. That happens at the presentation layer. But at the application layer, what you do is you wrap your stuff according to the maybe HTTP. You get there and you say you must represent everything as a header, the body, all those things happens at the application layer. That's where the protocols, how you structure HTTP request is captured there. Presentation layer, we deal with a few challenges of how do you convert the HTTP request into binary format that the computer understands. So you come and deal with the character encoding, we deal with encryption, we deal with compression, and then once you're ready, you pass it down to the session layer. The session layer ensures that you maintain sessions, like if you're browsing on your laptop and you have 2 tabs with YouTube, same machine, same everything, but the sessions are different. So you're able to track this data is supposed to go to which session. And then transport layer, that's where we break the stuff into segments and we send it over the network. Once we send it over the network on layer 3, the work of the network is to ensure that you pass the data from one router to the other and as you continue. So addressing comes here and everything that we deal with comes there. But once the data has been given, the source IP, the destination IP, it's taken to the data link layer that determines which interface or which link you're going to use to send the data. And then finally, we go to the physical layer where we decide how we are going to represent those ones and zeros as either electrical signals, fiber light signals if you're dealing with fiber, or if you're dealing with wireless communication, how they are going to be represented as waves. So essentially, that's what each and everything the OSI model specifies. And I know you guys know that. So I'll not focus so much about TCP/IP and what you can do and the protocols that deal with all these things. Like we know for sure that IP layer deals with the hop-to-hop routing. So one packet comes, you decide whether it will go to the next router, and you decide that based on certain rules. If a router is dead and that packet cannot be forwarded, the network just ignores it. Or maybe the user has made a mistake and the routing rules are very bad and you end up with a packet going in loops. So the network can decide to discard that. But then at the transport, that's where now we deal with the reliability. What if the network discards a packet? So TCP talks about things like retransmission, and every packet has to be given a sequence number. So we deal with the reliability. And finally, we have STP, which addresses some of the challenges that TCP had, and it is suited for telecommunication signaling, which is supposed to be very reliable. So when I look at the SS7, so the way you had the physical layer here, and you had protocols like Ethernet and other standards that are used on layer 1, The same thing happens for these guys. So you have MTP layer 1 specifies how the data is sent. You'll hear things like E1, how messages are supposed to be sent over the network. So those frames that we send over the network, layer 1 deals with it. Then layer 2 deals with the link. So you can associate, you can come up with the links from one node to the other, so that you use that link to carry the data. So, and then layer 3 deals with addressing. So in SS7, there is, in this diagram, you might see layer 3 having MTP3. It's actually message transfer part, layer 1, message transfer part, layer 2, message transfer part, layer 3, and we have other layers on top. So if you're going to build an SMSC or a HLR or an MSC dealing with SMS call flow, we need to deal with these map requests. So we need to implement map applications, which is mobile application part. Don't worry about the acronyms. So since the map request is carried within the TCAP payload, so you have a TCAP header, then the body is the map message. Then the TCAP is carried on top of SCCP. So you have the SCCP header, then the payload is actually the TCAP message. And then you continue all the way the MTP3, you have the MTP3 header, and the payload is this. So one of the things that you'll hear when people talk about layers, it's just a simple concept. You had your initial 2 bytes, but you start adding layers that are meant for controlling how the message is processed at each and every layer. So every layer comes with a certain header, and that header, everything that you put in that header is represented quite well. So we have that. So you can see this, and it tells you that this is how SS7 works. So we don't have MAC addresses in network elements that used to work in the telecommunication. But one thing I'll tell you is that when the IP network rose, and one of the things you need to know, SS7 came before IP came. Telephony was there even before the internet came. So this protocol was way before the TCP/IP was adopted. So then TCP/IP became so popular, and there was a need for us to make all our networks IP based. Like I know Safaricom a few years back, more than 8 years or 10 years back, they were getting into a project where they were making everything IP. So all network elements there, they communicate over IP. But then for you to communicate over IP, and you need to carry SS7 messages. So what needs to happen? And this is why SIGTRAN was introduced. So if you look at the OSI model, this is how it looks. At the network layer, you can see this diagram is more accurate. MTP3 deals with some of the network layer functions, but SCCP also deals with some of the network layer functions, and somehow deals with some of the transport layer functions. That's why you can see it represented as a big bar that cuts across 2 things. And for those guys who will be reading, you'll get to hear that. Now, the key idea is for you to do MTP transmission of data, you needed specific hardware, boards that were actually created for telco signaling. And those boards are very expensive. But because now IP became popular, IP now means that we can use even our laptops. And this is where now the changes came to be. So when you talk about the physical, this physical was replaced with essentially the IP network. So you carry IP packets, but then at the top there, you carry SCTP. So SCTP is the transport layer protocol that carries the SS7 messages. And then because you need to carry a map message and you don't have MTP 1, 2, and 3, below there you have an IP network. So what happens is that SCTP becomes the transport protocol that we use to carry the messages, but we must adapt them accordingly. So if you want to carry MTP layer 3 message, then SIGTRAN came up with a way of us representing MTP3 data, but then we call it MTP3 user adaptation. So basically what we do here is we adapt the original message and we specify how the various parameters are supposed to be carried so that we can interface with the IP layer, which is the lower layer. So essentially, instead of requiring us a very specific machine that can support this MTP stuff, you basically get a normal computer that can allow us to create these applications. So this is good news for us developers because we know how to write TCP sockets. We know how to write UDP sockets, and we can actually learn how to write STP sockets. Once you get the STP socket, the payload you get is basically the M3 UAE header, the CCP header, the TCAP header, and then the map message that you want to send. So if you're able to receive those series of bytes that we can see, and those series of bytes, now we decode them accordingly, we'll have created applications that use these. MAP, USSD gateway, SMSC, they work like this. HLR, they use MAP. These ones are used for other things, don't worry. ISAP is used for calling. So in the event we want to do calls, if we have implemented M3UA, M3UA, and then we come and do ISAP, we can start handling calls in a telco network. So basically, that's what you need to know. And I do not want to go down here and tell you so much about IP layer and everything that happens, but I'll just illustrate something very small. You, as a developer, when you want to make an API call that is called Natujenge product.php that takes two parameters in JSON. When you write the message in HTTP, which is a layer 7 protocol, this is how the message looks like. Now, this data, for us to send it over the network, it has to be represented in this format. So you can remember the body that we had here, these characters here, they are represented as 27 bytes, and then we add the HTTP header like that. But for us to send the data through the network, at the session layer, there is nothing we are adding in this case. But for us to send the data over the network, so we have the original JSON represented in nibbles, for those of you who have watched those videos, and then you have the HTTP header. So you guys can see why HTTP is not used within the core network. Because imagine you had 27 bytes, but the HTTP header was 437 bytes. That is communication overhead, which is so heavy. So the key idea is the protocols that we're going to look at, they don't send that much data. They send less data because you're able to optimize them and not send a lot of white spaces, a lot of unnecessary stuff. But this is going to change because the network is becoming super fast. Disk is becoming available. So the considerations that we needed to make earlier when we wanted to save the bytes on the network, it's not too important now because you can do 10 Gbps or 1 Gbps. So it's a trend. It's a thing that, yes, it was a very common thing for us to optimize how much data we send over the network, but it's becoming less important as we move on. So you can think of it as the original message, the HTTP header, the TCP header, and then the TCP header, the one that I've displayed here, is represented like this. And for those of you who did the first series, you don't have a challenge decoding a header. That's the assumption, because some of you did very well. If I gave you CD and BE, and I told you that the first 2 bytes, CD and BE, they represent the source port, you guys are able to compute and see that the source port is 52670. So even in SS7, at the network layer, this is where we add the headers, the IP, source IP, the destination IP, and you can see the same information being added there. So when people tell you SIGTRAN and it's a protocol stack, just think of it this way. We're just telling you that the data will be sent as many bytes like you're seeing on the screen. And those bytes will be split into sections. There'll be headers, there'll be M3 UA header, there'll be SCCP header, then there'll be a TCAP header, then there'll be a map header. So technically the same stuff we are seeing in IP where we talk about your JSON, the HTTP header in the lighter blue. Then you have these, I don't know whether this is brown, yellow. That's the TCP header. And then finally, we have the IP header. And this IP header, the first objective I had when I did the series on Love the Bytes was to make you guys not fear these hexadecimal characters, or what we call hexdump, because they're not complex. So you just start processing them according to the specification. Then after that, we take it to the physical layer, where we talk about, the MAC address, media access control with collision avoidance or collision detection, a lot of stuff concerning how you will send the message from one thing to the other, how you will do, those verification that the data has not been corrupted over the network. And then finally, we send the data as signals as a frame as we continue. So you can see how all the headers, you as a developer, don't worry about people saying headers. Just think of them as a series of bytes you receive over the network, and each and every component, you can break it according to the specification. And that's the only thing we need to do. But now not for TCP, we'll be doing for SS7. So I have created a folder, which I'll share with you guys. And I have some sample TCP dumps. And I want to just demonstrate something right now on Wireshark so that you can see the kind of stuff that we are talking about. So I have a message. This is a SIGTRAN message, and you can see how those layers come into play. So you'll be able to see these things. So remember, we said it's SIGTRAN. It's actually SS7 message carried via SIGTRAN. And how do you verify that? It's because at the bottom of it, you can see Ethernet, the source MAC address and the destination MAC address, IPv4 and stuff like that. You can also see IP address. Yeah. So you can see the source IP and the destination IP. Don't worry about this. And we also have the stream control protocol. This is the equivalent of the TCP source port, destination port. All these things, don't worry, you can learn them. And then finally, this is where now this diagram that we saw comes into play. So I will go back to the slide and just compare this with this as I come to a conclusion. This is the thing that we are calling the SIGTRAN stack, which is a way of us developers who can write IP-based applications to carry telecom messaging or signaling messages. So you can see at the bottom there we have the physical, but the physical here, it's basically the IP network. You can see it's the frames, the Ethernet, and the IP protocol that we deal with based on the TCP/IP protocol stack. Now above it, you can see STP. So you can see STP, which is like IP. You talk about the source port and the destination port, and verification tags and data chunks and all that. Don't worry about that. If you have to learn about that, we will have a group focus on that. Then above it, and I want you guys to see that everything that is sent over the network is actually 218 bytes, which are here. You can see all of them here. But the first 14 bytes, it's the data link stuff and the Ethernet stuff. And then you can see 20 bytes, they are for the IP header. And as you guys are familiar, 4 bytes, if I click on the IP, you'll see these are 4 bytes. OA 0529B1. 4 bytes are the source IP address. And then we go to STP, which is essentially 44 bytes. So our message is becoming bigger. And when we get there, we have now the MTP. But now when I look at the MTP, you'll actually see that it's the MTP3 user adaptation layer. And it has data parameters that you have to look at. And it has the protocol data, which is 1999 bytes. And that protocol data is actually carrying an SCCP message. And that SCCP header, you can see how the header, we can move to the header until we finish this. So when you're dealing with SCCP, we are calling the calling party and the destination party. So please note, we said that SCCP talks about, instead of IP address, it talks about the calling party and the destination party. These are called GTs, something that you're going to learn. Instead of IP address, we talk about global titles. At the MTP3 layer, we talk about the point codes. So here we talk about point codes, which are the logical addresses of a computer. So you can think of point codes as the equivalent of the IP, or sometimes you can think of the GT as the equivalent of the IP. And then all the information is specified as we have specified. So we have the calling party, the call party. Under it, we have the TCAP message. And the TCAP message allows us to carry begin, which is the transaction ID, 4 bytes. Then you go the source transaction ID, which is another 4 bytes. You continue like that, you continue like that, until finally you get the last part, which is the GSM mobile application part. So when you hear map, it's mobile application part. It just says how that message will be. And for some of you who are curious, you can actually see that this is a request that we are asking the location. I know this is not very clear from this dump, but we are basically asking, an SMS came to the SMSC, and the SMSC is asking the location of the user. And the response, you get the switch that is serving the user. And once you get the switch that is serving the user, you can talk to the switch that you got and you forward the message. If you want to see the message that is being forwarded, definitely we will go to the map part and look at what is there. It might sound like Greek, but all we need to do as developers is to mimic something that looks like this. And this is called the sending routine information for short message. And we got the response. And then finally, we forwarded the message. You can see forward SM, which is what MT forward SM. And you can see we are using SMS deliver. So when you go to the SMS deliver, you can actually get the message that was actually sent to that. And then finally, you can get the result that tells you that the message has been forwarded to the switch, and most likely it's being forwarded to the customer. So I know I've talked too many things, but all I want you to remember is this. If you're getting into SIGTRAN development, we cannot run away from analyzing the bytes. Whether those guys tell you layers, just understand that it's just a series of bytes that have information, and the documents, the specification documents specify how you're supposed to interpret that information. So you can know that if I get the SCCP header, the first part, what does it mean? The second part, what does it mean? This is something that some of you did when we did the last hackathon, so it should not be a big challenge. So thank you guys, and have a lovely evening. It was nice having you guys, and I really appreciate your support, and I hope that we will continue in that spirit.